Whether my screen is visible?
Yes, sir.
Okay. So does anyone of you have any query from the last class, whatever the concept we covered last class? Hello? Hello?
No, sir.
Okay. So probably you've not started reading yet, okay? Fine. So we'll start another module today, and that is basically the perceptron, which is also called the first generation of neural networks. They were the first one. Based on that, neural networks got built up and the state where we are today. So today we'll talk about this one, and it will conclude this module today itself. So it's a bit mathematically intensive, but not very complex at the same time. It's quite easy to comprehend whatever we'll cover today. So before I talk about this perceptron, and which was given by Frank Rosenblatt in way back in 1960s. So let me tell you this a basic standard paradigm for statistical pattern recognition, how normally happens. So in a statistical, when you go for pattern recognition and what people do. So they try to convert the raw input vector, whatever the raw input or different attributes are there, into a vector of feature activations or features, you can say that, features. So when I say features, it may so happen that multiple attributes constitute one particular feature. This is also the case maybe. And this features, how they can be always either a program can be written or they can be hand engineered. And this is how the features you decide. Once you have the features with you, then try to learn how to weight each of these features to get a single scalar quantity. When I say single scalar quantity uh, and weighting of the features, what I literally mean to say that suppose 8 to 10 features are there and you are based on empirical or some statistical analysis, you will come to know that this feature is more important than the other one, and based on that certain weights you found, and this is what. And if you're able to know this, you will be able you have to find it out the way that how can I go for a scalar quantity, and if this quantity is above some threshold, then you decide that the input vector is a positive example of the target class. When I say positive example or negative example, what I literally mean to say that when I say that this belongs to apple class or this belongs to guava class. So if I'm looking for this to be apple, and if it is, then I'll be calling as a positive class. Otherwise, the input sample is called a negative class. Okay. And so this is what the basic paradigm of this statistical pattern recognition happens. And if I go for this a diagrammatic approach, so this is what you have. You have all the inputs, attributes, and you have hand coded or found some sort of features units. And those features unit, you will also know how those weights are given to that, means which features are playing which significant, which are less significant, etc. And then finally you decide. So this is a basically conventional approach in case of a statistical pattern recognition. Now the question comes, why I'm saying this now? What does it have to do something with the perceptrons? So hold a minute, I'm just coming to that how this particular structure is almost asymptotically similar to or very analogous to the perceptron. So before I go about this perceptron, so basically the formative years of neural networks, when I say formatting, from the right from the it's a seminal work from Mac-Spritz and all, which who gave this idea in 1943. They come out with a that they hypothesized that a neuron is basically can be modeled as a computing unit. So they were the first one who said in 1943. Though neuron study was done by us R.Y. Kazel way back before and Pitt's model itself, but that was basically completely biological work, neuroanatomical work. And then this Hebb came, and this Hebb rule, where if you remember, I talked about something called Hebb rule. Uh, this is how basically it's used in auto association and hetero association for pattern association technique, and I did solve one problem based on that. So Habermas came around way back in 49, and he postulated the first rule of self-organizing learning, means how learning happens. And basically he gave the idea, means or some sort of hypothesis that how the learning actually happens in the brain, and they try to give a model to the in a algorithmic approach. And then this around 60s, or you can say exactly 58, Frank Rosenblatt, he proposed basically a concept of perceptron, and basically the first model of supervised learning he talked about. Even though McLespitz in 43 they talk about a neuron as a computing unit, but finally he gave a formal shape to it in Rosenblatt. Basically, he was a psychologist and mathematician as well, and he come out with this. So he gave this idea way back. Now, so these are the basically formative years of this neural network. And then in 60s, Woodron-Hoff came this concept of adaptive filters using least mean square algorithm, which is also called delta rule, which we'll discuss subsequently probably in the next class or so. So these were the some of the basic milestone work in the neural network. And when the perceptron, if you read the chapter on the in Simon Higgins book, they call as Rosenblatt perceptron. Actually, it's just a perceptron. So following the inventor's name, they gave it chapter name as Rosenblatt perceptron because there are many variants later came. So that time, Rosenblatt claimed many things about this, means how learning can happen, what it can do, and what all those things. Many things, very promising idea was there. Then around 1969, one person from MIT, that is Marvin Minsky and Peppert, these two people come out with a book, and that book they investigated a lot regarding the what perceptron cannot do, and they found out the limitations of that. And those people who are at the peak of their career, you can say that Marvin Minsky died some 2 years back recently, and he was that time of an AI was you can pioneer in the world. You can say that effectively he said that, and those people Minsky and Papert said that what is the limitation with the perceptron, but they never said that these perceptrons are useless idea. But somehow the community of machine learning and these people, they thought that because these are the pioneer people who said that the limitation, so somehow a negative signal spread among the community. And this negative means people thought that perceptron is not a good idea to work on or to take it out to investigate further. As a result, almost this research of neural networks was almost 30 years behind it pushed. So not much work was done during that particular time. Otherwise, you can imagine that this could have been more advancement. But of course, due to the computing unit unavailability, it could have been almost the same stage what we are today. But till another 30 years, not much progress was there. This was regarding the history of perceptron, how it came into. So basically, when you see this, perceptron is the simplest form of neural network used for classification of linearly separable pattern. Remember that here this word linearly separable patterns. So they are not meant for the data set or pattern which are non-linearly separable. So what do I mean by that? I'll explain in a couple of minutes now. And so remember that it consists of a single neuron with adjustable synaptic weight and bias. So entire perceptron, it's having this one. It's a single neuron system, and of course bias will be there. And as is mentioned that it's built around a single neuron is limited to performing pattern classification with only two classes, but it can be extended to more than two classes. Possibility is there by adding some more neuron, we can go for this, but provided that even the other thing should be linearly separable. So this what I mean to say when I say that they should be, they are meant for linearly separable. So here what I go for this to explain what is the mean by that. Yeah, this. So let's say this some sort of a plot you have, data plot you have, data you have, which you have plotted. Let's say just 2D data I'm talking about. Suppose this kind of data is there with you, and then if you're able to draw something and find a decision boundary between the two, a clear-cut decision boundary, then what you call it is linearly separable. So basically, one particular neuron or one perceptron can be used for classification. Only these two class classification. As I said, it can have a multi-class classification also possible. So how do you do that? In that case, possibility that there is some another sort of data set here, some maybe, and if we could do something. So this is also possible. But remember that whatever the classes may be, more than two classes, but the requirement is that they should be linearly separable. Means the data setting should be that we can draw a straight line through this, or you can say decision boundary, linear boundary. If that is the case, then this job can be done by a perceptor beautifully. Otherwise, it cannot be. Now more on this in a couple of minutes now. So this also we have to consider that perceptron uses Macclesfield's model for a neuron. When we say Macclesfield's model of a neuron, what do you mean by that? Anyone? What do you mean by that? Hello? Anybody? Well, so when I say this, a perceptron uses Macclesfield's model of a neuron. So we have already studied what is Macclesfield's model. Macclesfield's model is nothing but a single neuron structure you have seen, where the activation function is a threshold function, or you can say a binary level function. Means the value, if the activation potential is greater than 1 or is positive, I should say, then it outputs 1. If the activation potential is negative, then the output is 0. That's all. So a perceptron is making this use of this kind of neuron or activation function. So this is what diagrammatically it looks like. So you have this kind of this input attributes and weights are there, and this is the bias. Here we have your activation potential, which is nothing but the combined linear sum of this input, linear combination of that, along with the bias. And this is the activation potential, which is nothing but hard limiter. When I say hard limiter, means between 0 and 1, the value will be 1 if the value is positive, is 0 when the value is negative, the input is negative. And this is the output. And if I write this one, the entire sum, so it is nothing but Wixi plus B. And if you remember that, we were saying the notation, as I said, that we'll be using the notation WJIXI. Why I'm not using that WJI? Any idea why? What could be the reason for that? No? Speak out, man.
Because the perceptron involves a single unit,
Neuron.
neuron.
Yes. Yes, good. So because perceptron have a single neuron, so that's why there is no need to mention WJI, because there is no concept of jth and kth neuron. There is only one neuron. Okay, fine, good. And here, if you see that I have mentioned phi v, so basically it's a +1 -1. So even though I said it's a hard limit, but it's a binary hard limit. Means it is quantized, the value is greater than 0 as a plus, and if it is less than 0, so -1. Actually, if you are truly using thresholding function, then it should be 0. But however, if you want to quantize between -1 and +1, then this is it is nothing but the signum function. Okay. So goal is to classify input vectors into two classes, either +1, a positive class, and negative class. When I say +1 and -1, so whatever the label you want to give it to them, you can give it either mango or papaya or whatever it may be, right? But we are just mentioning this particular label. Now, to get this insight into the behavior of pattern classifier, we need to plot a map of decision boundary, that how an m-dimensional signal space is spanned by basically m input variables. So here x1, x2, or xm's are nothing but different examples. Each one of them we have some m-dimensional inputs, and how they are going to plot it. So in the very simplest form, there are two decision regions separated by hyperplane. Now see, when I use this word hyperplane, when we say the plane, so you know that it's basically two-dimensional thing I'm talking about. When I say hyperplane, we say multi-dimension. So the decision boundary is defined by this one, this particular thing. Means whatever the input comes as activation function, this entire sum equated to 0, and this is how decision boundary is obtained. And also there is one more reason for this, and at the decision boundary, the weight space is always perpendicular to the pattern space. So here, and due to this, it is basically nothing but orthogonal. So we can say that if I write this entire part, if W also I subsume into it, and I start from I equal to 0 to M, you know that when I consider a bias, so bias can be fixed as the input where X0 is always held at +1 and B is another weight W0. So I can write entire thing I equal to 0 to M W0 Wixi, and Wixi instead of sum we can always write in a vectorial notation W2x. When I say WTX equal to 0, so what do you understand about of it? Hello? When vector WTX equal to 0, what do you interpret out of it?
Dissimilar vectors.
Okay, so they are basically not dissimilar here. Of course, you can see that meaning, but here they are perpendicular to each other. The orthogonal, basically they are orthogonal. Remember that I was talking about the orthogonality in the linear algebra part itself. And of course, these are dissimilar. So here what I mean to say, at the boundary, at the decision boundary, the weight space always points 90 degrees to the pattern plane. And this is why we always equate to 0. This is the reason behind that. And so this is what it simply says this, okay, this is the perceptron. And that's a very simple, this is how in two classes, a decision boundary will be there. And one belongs to class C1, another belongs to class 2. Either way, it could have been either this way or that way. So this is just a representation of that. So when I was talking about this decision boundary, linear and nonlinear, so this is what I literally mean to say. You have a data space or your data which has some particular formation, another formation. If there's a possibility for you that you can draw a decision boundary, a linear decision boundary. So this kind of classification problem you call as a linear classification problem. However, if you have something like this, there is an overlap because this part is little overlapping in this particular zone and this part is in this. So I cannot draw a straight line boundary in this. So this kind of problem will be called as a no linear separable pattern. And any permutation or combination, this can be drawn in a very simplified way. The example which I use in the board were very simpler of this kind of nature. And this kind of thing, most of the time, in reality, it happens in the no linear fashion only. Now, there is a beautiful theorem here, but of course, unfortunately, I will not be able to prove for a simple reason that I'm asked not to ask the proof. So I'm not going for the proving this. This is called perceptron convergence theorem. So perceptron convergence theorem says that if the pattern or vectors used to train the perceptron are drawn from two linearly separable classes, then the perceptron algorithm converges and positions the decision surface in the form of a hyperplane between the two classes. And the proof of this convergence of this algorithm is known as perceptron convergence theorem. Now, simple idea is that a training vector is given to you, provided those data set have data which have the linearly separable patterns. If that is the case, after certain training, this perceptron algorithm converges. Converge means the weight space stop updating, and then you are able to find a decision boundary in the form of hyperplane between the two classes. You'll be able to do this, and this is done beautifully. Even even Google also in some aspect of that, when they have to study this, learn millions of parameters in such kind of setting, they use the perceptron, which is very simple to work it out. Even till today, it is being used, and that's why it is so important. Even though it belongs to the first generation of the neural network, it is still being practiced now. Now, before going for perceptron convergence theorem or the algo which we talk about, a little notations let's very clear. Because we want to learn this bias automatically. So to make this a simple fact, we always know that it's basically a simple trick that okay, a bias is there. So whatever the bias, if I know is fine. If not know, I'm considering W naught as some weight, which is equal to B. But always I'll fix X naught as a plus one. I'll hold it at this one. So this entire thing, if I can do this, so I can write the summation Wi xi, this entire part. Now, when I do this kind of setting, so my xn, that is the vector space, is becomes basically m plus one dimensional. If it is actually m dimensional, so because of inclusion of this bias concept, it is plus one is added always, so it becomes m plus one dimensional. And weighted space is also becomes m plus one dimensional because actual weight is from w1 to wm, but you have taken b as also as a part of learning, so which is nothing but b of n. When I say b of n, it means that bias at the nth time instant. Okay. So this is just a notation we'll be using and get comfortable with this. Now, linear combiner output is written as. When I say linear combiner means here the output, what is the v value? So I have missed here. It should be I equal to 0, 0 to m wi xi, which we can always write in vectorial notation as wt xn, right? And remember that it is just a nth time instance, or you can say that. So there is another a related theorem in this, which we call as fixed increment convergence theorem, which is very much part of the perceptron convergence theorem. So it says that let the subset of training vectors C1 and C2 be linearly separable. Means you are making this kind of assumption. The patterns are linearly separable. If this input presented to the perceptron originate from these two subsets, if it is so, the perceptron converges after some n-naught iteration, in the sense that when I say converges in the sense that after means 10th iteration or 20th iteration means whatever the value of keep on iteration, the value, the weight space, the value weight will remain same. It is not going to change. This is what you mean by conversion. And in the sense that this is the n is a solution factor for n naught greater than n max, means we don't have to keep on going. It means it has converged to that. So now perceptron convergence theorem says that basically it's almost guaranteed that if the linearly separable patterns are there, then it guarantees that they will converge and it will classify, it come out with a decision boundary. Always it is the case. So as I told, there is a good amount of derivations which I'm not going to. So I will come directly to the perceptron convergence algorithm itself. So algorithm has many components here. And so let's go one by one. So first we'll talk about variable and parameters. So variables here is the input parameters. So you say xn, so as I told you, because of bias, this plus one is there. Otherwise, this x1, x2, xn's are the actual attributes of your input space. Okay. Likewise, you have wn where bn is due to the bias, which you are also learning. And this is the case. And then finally, bn is bias. It's mentioned bn is bias. If you know the bias, fine. Otherwise, you can start from nothing and it will learn its own if there's a bias in the data itself. And yn is actual response, of course, quantized. And dn is a desired response. This is also quantized. When I say yn is an actual response and desired response, remember that when I say yn means the actual input you are giving and what is the output you are getting it. So it is like you are not taking the labeled value, and dn is nothing but the desired value which is already given as a part of the data set itself, which is a part of training data itself. Okay, so that is a desired value. Also, when I say this term quantized response or quantized desired response, so here for quantization means we have to approximate to the nearest value. So because in case of perceptron, it uses this Maclaurin-Spitz model, which is nothing but a thresholding function. So it is quantized to plus 1 and 0. So instead of plus 1 and 0, because you're talking about positive class and negative class, we have taken a signum function. So value is either plus 1 or minus 1. Okay. And desired response is also quantized accordingly. It means a label is either plus 1 or minus 1. And eta, there is a learning rate parameter. So there is a great deal of discussion about the eta value. We'll talk about later. For the time being, you can say there is some constant factor. It's just like a step. means with what rate the iteration moves from one step to one iteration to another, means how the learning changes. Okay. And remember that eta is always between 0 and 1. So this is the value for this. And then there is an initialization phase. So initialization phase means, because when you start this learning process, suppose you have data set at your disposal, entire supervised learning data set, and you want to train a perceptron. So you don't know what is the actual values are lying over there. So initially you fix all W0 equal to 0, all these things, and perform the following computation. But normally when you say that, man, okay, W0 equal to 0, then all are 0, the final value will be 0 only, right? So, but remember that there's a bias component. With that, some value will be there, and that will propagate or proliferate through the process. And then there is activation. So at time step n, activate the perceptron by applying continuous value input vector xn and desired response dn. So effectively what I'm trying to say that, if you remember here, this we said that wi xi z I equal to vary from 0 to m, whatever it may be. So initially all weights are 0. Initially weights are 0, but there must be some bias which may not be 0. And based on that, you are finding this and you are going for the activation function, that is y of n equal to, you can find phi v of n, you can give it, right? Based on that, so this value will be non-zero, even though others are 0, but due to the bias factor, this value comes out to be a non-trivial value. As a result, again, some quantized value will carry. Okay. And then you have this desired one, this desired response, which is given to you. When I say it is given to you, so remember that it will be, your data will be given in this particular fashion, something like this, that you have a training data of form, let's say, xi di I varying from 1 to m. So this literally what I mean to say, and also it is mentioned, it may be mentioned that xi may be some 10 dimensional, and di in this case is of course just r1. Okay, means there are m number of training examples where each xi could be of 10 dimensional. It could be, or if you are not comfortable with this, let me say some 100, and here let me say put each xi is some m dimensional. Okay, means m attributes are there, and the output is basically only one, either +1 or -1. So for this kind of things, so based on this on, you'll be computing the actual output. Whatever the actual output comes, you're comparing with the desired output for the corresponding layer, corresponding training example, and see and do accordingly. So we'll see what is happening. So now computation of actual thing. So actual response when come. So basically the summation we don't have to take. We can take this inner product of WT and in Excel. Once we do this, whatever the values is given to a signum function. So signum function basically either you can say this way, or it's take only value between plus and minus. When the value is negative, this values comes out to be negative. The value is negative, -1. That is what quantized to -1. You are not talking about -2, -3, or -0.5. Everything quantized to -1. When the value is positive, it is quantized to +1. Now, based on this, what we do? How do we then we change the synaptic weight? When you change the synaptic weight, this has to be seen. Now see that. So this at the nth time instance you have this. You calculated the actual output. If this difference is 0, this difference is 0, means the actual output produced by the system with the current set of synaptic weight, and the difference between the actual output and the desired response, if you found that they're exactly same, then you don't change synaptic weight for the next iteration. It will remain same because this entire part becomes 0. Okay. Now, when this value comes out to be this particular term dn minus yn comes out to be positive, either it can be +1 or it can be -1, whatever. This comes out to be positive. Then what you do, you scaled version of the same patterns you add to the synaptic weight. If this value comes out to be negative, then some portion or version of this same pattern gets subtracted from the synaptic inputs, whatever based on that you started, and they get updated for the next iteration. And as I mentioned, dn is +1 when xn belongs to class 1 and -1 when xn belongs to class 2. So, and this particular process, very simple learning algorithm is there, very simple. If this particular difference is 0, you don't do anything to the synaptic weight, you use same synaptic weight for the next iteration. If the value is positive, you just add the whatever pattern you have to the existing synaptic weight space. If it is negative, then you subtract the whatever the pattern you have taken from the existing synaptics. And this simple process will help you to make it to the convergence, provided, remember that, provided this patterns are coming from the space which are linearly separable. And finally, we keep continuing this particular process. Once synaptic weight is updated, we go back to step 2 here and find this all activation function changes this one. Now here it will be wn plus 1, xn plus 1, signum function, yn. This process keep on iterating till you exhaust your training data, whatever you have. Okay. This entire part has been summarized in this particular thing, which I have written the same thing. Okay. So this is a simple table which I have taken from the book itself. And as you can see, m plus 1 by 1. So basically it is those many rows and this one if you're talking about. Similarly, the dimensionality of the weight space is also m plus 1 by 1. Does anyone of you have any question here? Means how this perceptron learning will happen?
So what does the N stand for?
N stand for the nth iterations. Iteration number you can say.
Okay, so
Suppose there are 100 examples are there in training data. So x1 means the first example, x1 means second example, x3 means third, like that, like that. Is that clear now? And here eta, it is not n. Here, eta is a basically learning rate parameter which always lies between 0 and 1. How to choose that we'll see in the next chapter or so. Any other question anybody have?
Sir, is perceptron only able to differentiate between two classes?
Yes, but we can extend to multi-class as well, as I shown the board. 3 class also possible, but remember that we have to ensure that whatever the pattern we are subjecting to the perceptron, those patterns should be linearly classifiable. That is a condition. That in that case, perceptron works beautifully. Otherwise, not.
Yes.
Okay. Anybody else? Fine. So now I'm moving to a little part of this, which is test your mathematical understanding as well. So basically there is some sort of relationship between a perceptron and a Bayes classifier for Gaussian environment. So we want to study what's the relation between perceptron and Bayes classifier. Bayes classifier is basically standard pattern recognition algorithm, you can say that. So we claim that we know that perceptron is a basically linear classifier. When I say linear classifier means some sort of equation of y equal to mx plus c is possible to derive in case of perceptron because they are linear classifiers, so they does it. Now the question comes, can I use Bayes classifier for the Gaussian environment where the data set follows the Gaussian distribution? If that is the case, then it has been found that a Bayes classifier starts behaving like a linear classifier, which is nothing but a perceptron, but under the Gaussian environment condition only. Okay. However, such kind of precondition we don't put it on the perceptron. We don't say that perceptron can go for linear classification only for those data which are Gaussian distributed. No, we simply say that whatever the distribution may be, only condition is that those data points are if they are linearly separable, then perceptron can do the job beautifully, 2-class classification. However, Bayes classifier in general, it can do the classification, but if the data are Gaussian distributed, then it does behave like a linear classifier. And this is how the perceptron. So we want to study that relationship between the two, and we'll see how. So that's why it's mentioned here that it bears certain relationship with classical pattern classifier known as Bayes classifier. So we'll do this particular process in two phases. First, we'll try to understand what is the condition for classification as per the Bayes classifier. Then we'll try to portray that if I incorporate the Gaussian environment condition in the Bayes classifier, how is classification condition changes, and if that happens, does it really behaves like a perceptron or not? When I say does it really behave like a perceptron, means whether it behaves like a linear classifier. So we'll see that. So when the environment is Gaussian, the Bayes classifier reduced to linear classifier, as I told. Also, linear nature of the perceptron is not contingent on the assumption of Gaussianity. As I mentioned, that when you go for the perceptron classifier, we really don't put this pay condition that it should be Gaussian distributed. It could be anything, only it should be linearly separable. Now, before that, we'll start with the Bayes classifier. Means try to understand the Bayes classifier itself. So Bayes classifier, or sometimes we'll call as a Bayes hypothesis, is a hypothesis testing procedure. Basically, we minimize the average risk R, and average risk R means some sort of function. A quantification has been done that if it is the value is this much, so what will happen if it is value is below or above, what it's going to be. So that is a hypothesis testing is going to be. So when you say hypothesis, this all looks very complicated, but no, very simple thing. In the 6th class science also books, they teach you something called scientific method. And those scientific methods are nothing but OQ hack. Simply acronym if I want to put it, OQ hack. OQ hack means you observe certain phenomena, you see that okay, this is happening. Then you try to question yourself, question why it is happening. So that you question. Then you try to hypothesize it. Means ki, it happens always the case. You see are under certain conditions. So that's your hypothesis. Then to test that hypothesis, you do certain experiment. And based on this experiment, if that particular phenomena happens under the condition which you stated, then you say that okay, hypothesis testing, it has passed or it is failed. And accordingly, you conclude something, right? So this is the simple process, what you call OQ hack. That is observation, questioning, hypothesis, experiment, and this one C is the basically conclusion. You should conclude yes, this phenomena happens or not. From that, you can see that. So this Bayes hypothesis testing procedure, we'll talk about something called average risk. So this average risk definition is given by Van Trees. So Van Trees has given a series of books. You can see that from volume 1 to volume 4. Basically, in ENC, we have studied this part. So, and those are nothing but detection, estimation, and modulation theory, particularly related to the communication theory, which is particularly on statistical communication theory. So the same idea has been taken from Van Tree's book, and this is what is called by risk. Now, what do you mean by the risk? Just hold on, I'll explain this. So let's say for two classification problem, let's say C1 and C2, class 1, class 2. The average risk defined by something like this, R equal to C11 P1 integral subspace L1. This is nothing but the PDF, probability density function, of the X, pattern X, given that it belongs to class 1. Similarly, C2, P2 and P2. Just hold on, I'll explain what you mean by all the C22, P2, etc. And let's say integral subspace L2 PDF of X, the pattern X, provided that it belongs to class 2. Likewise, now here if you see this definition, so we want to know first of all, this is a risk, but risk for what? Risk for what? So here we say risk for classification, correct classification or wrong classification. Means it's a pattern comes with what this one risk it is classifying correctly, or what is the risk for misclassification. So that is the risk. This risk ideally should be 0, means there should not be any risk Your system should be such that when pattern comes, it should clearly classify a pattern belonging to class 1 to class 1 and pattern belonging to class 2 to class 2 only. Now, so here this P1 and P2 are called prior probabilities. So let me explain this. So PI, this terms P1, P2, Pi is nothing but a priori probability that the observation vector x is drawn from the space Li. Li means means whatever two space I'm talking about. This is L1 and L2 means, and P1 plus P2 should be 1. So this is a prior probability, means what probability that belongs to class 1 or it belongs to class 2. And then Cij. So Cij, see very carefully. Cij simply says that cost of deciding in favor of class Ci represented by a subspace Li when the class is true. So when I say this true is, let me go back here. Means here if I say C2y, so it's basically cost of classifying a pattern in favor of class 2, whereas it is actually belongs to class 1. So this is the cost. What is the cost incurred? Similarly here if I say the cost of a pattern being classifying to class 1, whereas actually it belongs to class 2. So this is the cost. And when I say C22 and C11, it's very clear that cost of classifying into class 1 and actually it belongs to class 1 only. So you can see that this cost and this cost, so these factors basically measuring or introducing the concept of misclassification, means cost incurred in the misclassification, whereas this is the cost incurred in the classification. Now you tell me, any one of you, if you without any quantified this one, any rough guess, if I say C11, C22, C21, C12, comparing to C11 and C21, which should be high? Which cost should be high? Misclassification cost or correct classification cost? Which should be high? Anyone? Anyone of you? Hello? Just guess it. Any rough
Incorrect.
guess? Huh?
Incorrect classification.
Should be having high cost?
Yeah.
Yeah. So speak out completely, man. आधा खा जाते हो. So in this case, what is happening? So what you said is correct. So basically when you say cost, so cost means the cost to the system because you want to have some sort of a function which is going to punish the system itself. So you say that it's a costly affair. So basically you are misclassifying it. So it should be costly thing. So system should not behave that way. It should avoid this cost. Okay. So whoever has said is 100% correct. So and then the third component, fxxici, is basically nothing but conditional probability density function of the random variable x, given that the observation vector x is drawn from the subspace Li, right? So means it belongs to the same class only. So this is the probability density function, this is the prior probability, this is the cost incurred. Now things are clear to us. Now first two terms in equation 1, previous one, you saw that is represent correct decision, no misclassification, whereas the last two terms are incorrect decision, right? Now we want to determine a strategy for the minimum average risk. Our objective is to make this risk as minimal as possible. How do we do that? So what could be the strategy for us? So let's see that. So overall observation space, we can say that when I say observation space means the subspace from which the data is being drawn. So I'm calling L and equal to L1 plus L2. So when I say L1 means in observations in the vector space L1, all the data belonging to class 1 are line, whereas in observation space vector space L2, all the data belongs to class 2 are line. And combined thing I'm putting as a observation space L. Now this equation 1 can be written in the equivalent form. Remember that here it was L2 earlier. Here it was L2. Okay. So what we can say that because L2 is there. So either I could have written everything in terms of L1 or everything I could have written in terms of L2. I could have done that either way. So I've done everything in terms of L1 and L. So L2, wherever L2 was there, I can write L minus L1, right? So I've done same. Also, here it is very clearly mentioned, as somebody has correctly said, that the misclassification cost should be higher as compared to the correct classification. So we are comparing C21 with 1 means what is the correct classification it belongs to. Here you are categorizing into 2, whereas it is belonging to the 1. Here it is categorizing into 1 where it belongs to 1 itself. So definitely this cost is going to be higher than this one. Similarly, C12 is going to be higher than C22, right? Now with this kind of thing, now let's see what can be done. Also, we remember that in the entire vector space, you know that from the probability perspective, the CDF, or you can say that probability density function, whether it's conditional or not conditional, equal to 1. That is basically from the 3 axioms of probability, you know that for the entire space, this value, when you integrate it, it is going to be 1. This is in continuous in nature. If you say discrete probability, so sum equal to 1. Now, so with this condition at our hand, and with this particular thing, integral property of this one, a minus v fx dx, I can write a fx minus b fx dx. We can apply this. And with this concept introduced to this one, so we'll separate those individual components. So when we write it, so everything belongs something like this. So here what is happening that over the entire vector space, we know that this value comes out to be equal to 1. So only constant factor C22, P22 will be left. This will not be there because entire 1. Here, this entire part over this vector space L, this will become 1. So C21, P1 only will be left. Rest will be remaining there, will all belong to L1. So we have to find the factors and see what can be done. So by doing all these things, which I have just said in previous slide, by doing all this analysis or incorporating this PDF across this entire space, this becomes 1, this becomes 1. We have written this one. Again, we can rewrite it. So this factor plus this factor is coming out to be here. This entire part, we can put it in this particular bracket. So this becomes our integrand. So if you see this all in this L1 space with respect to dx. Now we can think of some strategy. What could be strategy to reduce the risk? Any idea? What could be the strategy to reduce the risk? You know that this is the fixed cost. You cannot do anything with this. You cannot do anything with this. Now everything depends on this particular integrand, whatever is there in the square bracket. If this value comes out to be negative, then that is a favorable part for us. Then what will happen? Comes out to be negative means if this particular factor is dominant, it is greater than this one, then only it will be negative. If this entire part is negative, means it will be subtracting something from this fixed value, and that's what we are looking for. The risk should be less. However, if this value comes out to be positive, means if this part is greater than that, then it will further increase the risk value. So we'll see this. Based on this, we'll talk about the strategy, means what is going to happen. So from this itself, we can make out this. When this negative term is greater, overall, this integrand value is negative and is reducing the risk. In that case, it belongs to C1. So we say that the pattern under consideration belongs to class 1 and it belongs to this subspace L1 itself. However, if this value comes to be positive, then what will happen that even though it belongs to L1 space, risk will increase. It means that it is misclassified and it should be labeled to class 2. But when this integrand value is 0, means whatever the pattern you are talking about, it can be assigned to either of the class, either C1 or C2. It doesn't matter if that is the case. So this thing, whatever I said it, Now let me put it in the words. So these two terms are fixed cost. You cannot do anything with that. To minimize the risk, we may reduce the following strategy from this particular equation for optimum classification. Okay. As I mentioned here, for all the value of the observation vector x, for which the integrand means the bracket is negative, should be assigned to space L1, right? That is class 1. For the integral would then make a negative contribution to the risk. Negative contribution to the risk means further something will be reduced. All the values of the observation vector for which the integrand is positive should be excluded from L1, should not be part of L1. That is, it should be assigned to class 2. For the integral would then make a positive contribution to the risk. If it is 0, as I mentioned, then it really doesn't matter. It does not have any effect on the average risk and may be assigned arbitrarily either to class 1 or class 2. We are assuming that such points are assigned to subspace L2. Either way you can do that. Now based on this, we'll try to put it across. We wanted to have it because we have taken something from L1 space. So we want this entire integrand to be negative. Negative means this particular factor should be higher as compared to this one. Right? It means P1 C2 minus C1 fx should be greater than this value. If this is greater than this value, then we can hold certain things. Then we assign the observation vector x to subspace L1 means it belongs to class L1, otherwise class 2. So this a simple rule we can make it. Now to formalize this much better, let's shoot the concept of this something of likelihood ratio. So let me define another variable called lambda x. This is capital lambda, and actually this is not small x, capital X only. Here also is a vector, not one particular instant. So this is the ratio of this likelihood ratio because this by this and this will go there, right? So this is called likelihood ratio because this is also CDF. This is also CDF, density function ratio. That's why we call it the likelihood ratio. And then it's called Z, Xi, but without Z also anything is okay, any symbol if you feel like. And because this came down this, so P2 C12 minus this one divided by this, so this is the factor. So you see that this is basically a constant value, whatever it comes. Based on this, we can write a simple rule for the base classifier. This how it should be. And as I mentioned, it's likelihood ratio and the constant function, which is called thresholding function also. Both quantities are positive, of course. This is also positive. This is also positive. Why is this positive? You know that C22 is the cost of correct classification. C1 is the correct classification. And this will be always higher. So this subtraction will be always a positive. Here also positive. Probability is there's no concept of negative. So this will be always a positive factor. This will be also a very positive factor. So those are positive quantities. So now we can make a decision rule here that if for an observation vector x, if lambda x is greater than z, that is this threshold, then we'll assign x to class 1, otherwise it's assigned to class 2. Right? This is what we do. So this thing in a comparator or more implementation perspective, we go for something like this. You have a module which is likelihood ratio computer, or you can compute likelihood ratio over this, that is lambda, and z you have already computed, and then you're comparing, and here you say the same thing. Then this x, the pattern is assigned to class 1 if lambda x is greater than z, otherwise it is class 2, assigned to class 2. Simple. Now because this likelihood ratio are basically most of the time this distributions are some sort of exponential function, so it is easier to deal with the log likelihood function. While log function, because first of all log is a monotonic function and it is not going to affect the actual behavior. Rather, it helps us to simplify this to deal with this exponential. So instead of taking simple likelihood ratio, we say log likelihood ratio. So instead of this lambda x, we say log lambda x. So when we take log to this, we have to take log to this as well. So in this case also same thing. If log lambda x is greater than log z, then we classify to C1, otherwise classify to C2. So this is another way of looking at it, one and same thing. Now, so this is what we have just now. We have derived the condition for a base classifier to work. So far, we have not talked about any perceptron in this. We have not talked about anywhere or any pinch of this Gaussianity into it. Now let's introduce the Gaussianity into it. We are going to talk about base classifier for a Gaussian environment. That if I consider my data to be Gaussian, then what is going to happen? So remember that if you remember that Gaussian distribution for one dimensional is, remember if you say that suppose something fx, so 1 by 2 pi sigma, you see that, and exp minus 1 by 2 x minus m whole squares. M is mean, or basically mu, I should say, mean. And this is how you have done it, right? Now this is when your data is basically one dimensional. But when you go for n dimensional or m dimensional, whatever, multi-dimensional, this entire game changes. This distribution function changes, but the overall structure remain the same. So we'll see that those factors now. So that's why I put it coded for the one dimension. So let's see that here what we go about it. So this consider again, we are considering two class problem, and with Gaussian as the underlying distribution, we are going to have it. So let's say a random vector x has a mean value that depends on whether it belongs to class 1 or class 2. But the covariance matrix of x is same for both the classes. What do you mean by that? That whatever pattern you have taken, it can have mean depending on that whether it belongs to class 1 or class 2. So different mean is required, but it can have the same covariance matrix. So what does it mean? Anyone? Formally, let me say this, that is to say, for class C1, so it is the statistical mean, E, we represent as statistical mean or mean by mu1, and it is covariance matrix, which is nothing but expectation of x minus mu1, x minus mu1, t, c. And for class 2, mean is different, mu2, and expectation is, of course, this is c. So surprisingly, this is expectation for, or the covariance matrix for either pattern 1 or pattern 2. There's either this class or this class remains same, but their means are different. What does it mean? Can any one of you tell me? What do you mean by that? Anyone? Okay. So let me tell you a very non-mathematical explanation for this, how I understood way back when I was studied this portion first time. So let's, instead of saying somebody else, let's take it on us. That Indians, either in India or abroad, Indians either in India or abroad, their behavior remains same, natural behavior. So when I say behavior remains same, I'm talking about covariance or the variance, how they are spread, the behavior, the pattern remains same. When I say either in India or abroad, means their location differences. You are in India, Delhi, or in Denmark. So these two locations are different. So basically your mu's are basically a location parameter, means where you are lying, right? Whereas variance sigma or covariance matrix C is basically a behavior quantity, how it is going to be. So what do you mean to say that? Let me say a very simple thing from a clustering point of view. It will give us some insight. Let's say I have a something like this. If I have a particular pattern here, this kind of, and let's say it's all plus, 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 this kind of data sets are there. and there is another cluster minus minus. So if you see that overall behavior of the data pattern here is also triangular in shape, here also in triangular in shape, but the location, if you see that this location is completely different than this particular location. This is what I mean to say. So it is possible that one particular data, when it belongs to class 1, it may having one mu, may have different mu, but covariance matrix remains same, means overall distribution, or I won't say distribution, behavior of the data, overall data or variance remains same. That's what I was saying this. Well, simple to understand, the Indians in India or abroad, their natural behavior remains same, right? So here in India, the location, abroad that location, but the overall our behavior remains same. So don't take it personally. This is I'm telling you some from understanding point of view only. If you understand this, fine. Now, once we have this particular fact here, now we'll go. Our journey is set now. So with this, so as I mentioned here, C is a non-diagonal, which means that samples drawn from class C1 or C2 are correlated. They are not independent. They are correlated, and it makes sense. Also, it is assumed that C is a non-singular. It means its inverse exists. Its inverse exists means rest of the analysis we can do. Now, a multivariate Gaussian distribution is defined by this. If X is a m-dimensional, what example I quoted on the board, that was for only one-dimensional. But if it is m-dimensional, so your probability density function becomes 1 over 2 pi m by 2, m whatever the dimension may be. So remember, if the dimension is only 1, so it is 1 by 2 root 2 pi, fine. Now here determinant C. So basically when you say one dimensional, there is no concept of covariance thing. Matrix, there is only the variance, that is sigma you write here. So instead of that, here covariance matrix is there and root of this one. Okay. Exp minus 1 by 2 x minus mu. So this is not only one x, basically is vector x, this kind of vector, and mu y. Mu y means it belongs to which particular class you're talking about. T transpose and C inverse x minus mu, because this is how you write it, and I equal to 1 or 2, because we are talking about two class classification problem only. That's why 1 and 2. Now it is assumed that P1 equal to P2 equal to 1 by 2, means the value which you are taking, the two classes are equiprobable. That assumption you are making, equiprobable, there's no bias in that these are more and these are less. So these are equiprobable, that assumption you are making. Also, we are assuming that the cost of misclassification are same. How much that is there, that doesn't matter. We have to just say that their misclassification costs are same, whereas correct classifications are same, and that is equal to 0. We are saying that when you're doing something, there is no cost for, no punishment for that. We have information to design. Now with all these things, like we have this multivariate Gaussian distribution, and we know what is a P1, P2, what is the cost for that. So we have sufficient information to design base classifier to two-class classification problem. Now, with this, first we find the likelihood ratio, that is lambda x. And lambda x is fx c1 over fx c2. So whatever the expression which we have wrote in the last slide, we'll write here 1 by 2 pi m c, basically determinant. So this bar is for that 1 by 2 and this particular factor. Instead of I, we are talking about class 1, so 1. Similarly for this, when you see that this particular thing is a constant factor, this we can cancel it easily without any reservation or any problem. When we cancel this, we have something like this, right? Now this is lambda x. Now you realize the power of log likelihood ratio, which I was talking about. This is the likelihood ratio, and we can go for log likelihood ratio also. With this also analysis can be done, but life will become complicated, unnecessary to deal with. With this, it is very difficult for me to show it as a linear equation. So I'll use this concept of log likelihood. We'll take the log of this lambda function. When you take the log of this one, so log of this entire part, so log m over n, becomes log m minus log n. You know that process which you studied way back in 10th or 9th. This one minus log this. Now log and exp, because remember it is natural log, so this and this get nullified. So finally what you get is this particular factor minus 1 by 2 x minus t c etc. and this particular fact. Okay, and remember that we simply cannot add them. You cannot do this. Now with this, we'll try to represent it. Now the question is, can I represent it as some sort of analysis? Can I do some further investigation into this? So the answer is very much yes, and we'll see this. Same thing equation I've written here. Now I'll try to break it up. And remember that there's some typos from my side, which I'll do here. Basically, it's a one particular vector, small x in bold. Here, if I'm writing capital X means entire matrix, so actually it should be small x in bold. So while sending you the handouts, I'll make this necessary correction. So when I do this, so how do you proceed? How do you further solve this problem? Any idea? Any one of you? Any guess what can be done? Hello? If I give this equation, how do you solve it? Further. Bolo bhai. Okay. You are busy. So what we do, the first point of attack for us is that, of course, let's say 1 by 2 I can take common without any issue, and this will be minus and this will be plus. Fine. What next I'll do, this t is there, so let me take this transpose, propagate it inside. When I take it, because I'm taking it inside, is just straight away I can say xt minus ut, u1t, etc. And remember that here mean is not a single element. This is also a m-dimensional vector, not a one single, because your x is a m-dimension. So this will be m dimensional. So this is transpose. I take it inside. Now I'll just multiply xt to this entire one particular factor, this to the entire one particular factor, and similarly to this side. When I do this, I get something like this. And this when you, so I have solved step by step. In he just write the formula directly. So go through this particular step carefully. So once we do this, and after doing this one, further we multiply this xtcx and minus plus, so all those stuff. And once we have this, finally we are writing this mu1 minus mu2 t, because those factors are there, because C inverse 1, so this particular factor is there, and somewhere minus 2, this was there. So we have written it in this fashion and this fashion. Here xt C inverse mu1 mu minus 2 is there. Remember, there we have to apply one particular trick. And trick is that either this I could have written in this form, or this could have been written in this form. Now the question is why I have to write this in form, not this one into this one. Because ultimately I want to show equation of a straight line, that is y equal to mx plus c. So mx, so x should come at the end. So the x should come at the end. So I have to transform this into this. And this is very simple. Basically a particular matrix here. And this is also a matrix and this is matrix. So whenever this is there, I can flip it. When I flip it, so this t comes to here and x comes without any t. So without this, dimensionality does not make any changes. That's the beauty of this. So if something of this one, whatever the overall dimensionality of this particular product is there, if I flip these two matrices and retain the transpose position, then my dimensionality of the overall thing remains same. So when I do this, and when I do this in this particular fashion, so I'm just flipping here. So this part and this part has become twice of this one and this. So this becomes something twice of this, etc. Now I'll take this 1 by 2 inside and cut it off. This 2 is just a this scaling component. So once I do this, I'll get something like this. So now it may not be very obvious to you, but actually it is. If I'm taking log lambda x is a y of x equal to, this becomes mx plus c. C, so here we will be calling as some sort of b vector, that is a bias. So this particular is, instead of mx, is nothing but wtx. So here, now when you substitute the value of P1, P2, C1, C2, etc. for Z, this log Z comes out to be 0 for a simple fact because P1, P2 is constant, 1 by 2, 1 by 2, and C1, C2, etc. These are basically C22 and C1 is a constant, sorry, 0. So left was C21 and C12. So C21 and C12 are the same, so they get nullified. So overall value comes out to be 1. So log 1 is 0. So log Z is 0. Now, from these two previous equations 7 and 8, we can state that base classifier from the problem at hand is a linear classifier as described this equation. Means if I write y equal to wtx plus b, compare this equation with this wtx plus b. So I'll find that y is nothing but I'm talking about log lambda x. W is nothing but C inverse mu1 minus mu2. Now you may ask question, man, here this was coming first, this was coming later, why you flipped? Remember that I'm talking about the inner product form WTX. So that's why here, if I take this transpose, these positions will change. So this will flip. X you cannot not supposed to change anything. This part is W. When I say WT, so T will be here and this position will change. So this is how C inverse, and B is nothing but the bias for this. So ultimately what we have shown that base classifier under the Gaussian condition behaves like a perceptron. Because why perceptron? Because it's just like a linear classifier. Otherwise it is not behaving, right? So now we can say that if the output y of the linear combiner is positive, assign the observation x to class 1, otherwise assign it to class 2. Same thing here, we are saying this positive only. Now there are certain observations to make and we'll just do this now. Perceptron operates on the premise that pattern to be classified are linearly separable, that we know that. Because if something are not linearly separable, we cannot apply perceptron. And here, the Gaussian distribution of the two patterns assumed in the derivation of Bayesian classifier certainly do overlap each other and are not separable. Completely, they are not separable, even if they are doing Gaussian thing. So see here. And this is what you mean to say. Gaussian distributions are there basically. And this I was talking about location. This is one particular location. This is another location, right? Location 1, location 2. But overall behavior, which is described by the covariance matrix, that remains same. It's not that this is more spread or more narrow. It is not like that. Also, basically this one, they overlap certain part of here. Even though this belongs to class 1, this may belongs to class 2, certain boundary is there where they are overlapping, right? So this part, certain part is overlapped here for class 2, here from here class 1, here class 2. So of course there is a some overlap and they are not completely separable. But when the inputs are non-separable and their distribution overlap, the perceptron convergence algorithm develops a problem because decision boundary between the two different classes may oscillate continuously. It keeps on coming here and there. There is no idea what is happening. So there's oscillations happens. So that's why it says that if they are not separable, then we cannot go ahead with the perceptron. It is not a good idea to go with the perceptron. Now Bayes classifier minimizes the probability of classification error and it is independent of the overlap between the distribution. So that's the beauty. It tries to positions in such a way that this misclassification error reduces. It cannot say it is 0 then, but it reduces. Try to minimize in that way. That is the beauty and design of the Bayes classifier itself. So perceptron convergence algorithm is non-parametric in the sense that it makes no assumption about the form of underlying distribution. As I said, we don't say that in perceptron is linearly separable if and only if the underlying data has so and so distribution like Gaussian distribution. No, nothing of that. So that's it. That's why I say it is non-parametric, whereas Bayes classifier is parametric. We say that Bayes classifier behave like a linear classifier if and only if the underlying data set follows the Gaussian distribution. Also, the perceptron convergence algorithm is both adaptive and simple to implement. You saw that it's very easy to go ahead with. The storage requirement is confined to the set of synaptic weights and bias. Whereas design of bias classifier is fixed here. It is not adaptive. It's not adaptive very often. And it can be made adaptive, but at the expense of increased storage requirements and more complex computation. So this is all about the perceptron. So you can expect some particular problem based on this. So you apply this perceptron convergence algorithm based on that and find the synaptic weights after a few iterations. If you are asked to find how many iterations you are. If you are free, take any linear classifier data set and code it either in PyTorch or TensorFlow, whichever, and see how many iterations it takes to learn the proper classification. So I'll stop here.
Excuse me, sir.
Yeah.
What do you mean by adaptive when
Huh.
Septon is
Adaptive.
adaptive, Gaussian is not?